So, unit 2, second law, entropy and availability. This is engineering thermodynamics second unit. So, here we discuss about the second law, entropy and availability. So, introduction to second law. So, according to the first law of thermodynamics, all the form of energy are equivalent. So, one form of energy can be converted into another form, as we know all about that. So, also in a cyclic process, the heat is fully converted into work, that is called vice versa, but in actual practice all the form of energy cannot be changed into work. Some amount of energy will lose in every stage. Hence, there are a certain processes which are not possible to occur even though these processes do not violate the first law of thermodynamics, right? So, further, first law of thermodynamics establishes equivalence between the quantity of heat used and the mechanical work, but does not specify under the conditions which conversion of heat into work is possible. So, neither the direction in which heat transfer can take place. This gap has been bridged by the second law of thermodynamics, that is called introduction. So, we go for the performance of heat engine and reversed heat engine. So, what is meant by heat engine? So, heat engine is used to produce the maximum work of heat transfer from the given positive heat transfer, right. So, the measure of success is called thermal efficiency of the engine. It is defined by the ratio. So, we have to measure the efficiency of the engine can be defined as thermal efficiency. So, thermal efficiency is eta thermal efficiency equal to work done divided by heat supply, that is called W divided by Q. So, here W denote the net work transfer from the engine and Q denoted as the heat transfer to the engine. So, here for reversed heat engine acting as a refrigerator, when the purpose is to achieve the maximum heat transfer from the cold reservoir, the measure of success is called coefficient of performance, that we denoted as COP, that is called coefficient of performance, right. So, we have to measure the efficiency of the refrigerator is denoted as coefficient of performance refrigerator Q divided by W, that is called how much amount of heat will input into the refrigerator and how much amount of work done supplied to the refrigerator, that is called Q, heat transfer from the cold reservoir, and W it is denoted as the net work transfer to the refrigerator. So, for a reversed heat engine acting as a heat pump, the measure of success again called the coefficient of performance, the ratio of coefficient of performance to the heat pump Q divided by W. So, Q heat transfer to the hot reservoir and W network transfer to the heat pump. So, this is the just a 2D sketch, that is called the layout block diagram for the heat engine, heat pump and refrigerator. Here first we take it as a, that is called heat engine, heat reservoir, heat engine, cold reservoir, and the second one is heat pump or refrigerator, that is called hot reservoir, heat pump or refrigerator and cold reservoir, right. So, this is the efficiency. So, the efficiency of the heat engine is defined as Q12 minus Q2 divided by Q1, that is the coefficient of performance of the refrigerator Q2 divided by Q1 minus Q2, and the coefficient of performance of the heat pump is defined as the Q1 divided by Q1 minus Q2, right. So, these are all the basic steps. So, next we move to the Kelvin-Planck statement and the Clausius statement. So, what Kelvin-Planck state that it is impossible for any device that operates on a cyclic process to receive heat from a single reservoir and to do the equal amount of work. Although Clausius and Kelvin-Planck statement appearance to be different, they are really equivalent in the sense that violation of either statement implies violation of other, right. So, what Clausius statement? So, it is impossible to construct an operating device working on a cyclic process which produces no other effect than the heat transfer of the engine, that is called low temperature body to high temperature body. In other words, heat of itself cannot flow from the colder body to higher body, that is called Clausius statement. This is the two major difference between Kelvin-Planck statement as well as class A statement, right? So next we move to the Carnot cycle. So nowadays we are using 2-stroke engine, 4-stroke engine. So all the engines operating by the basic principle of Carnot cycle. So what Carnot said, right? So the cycle was first suggested by the French engineer Sadi Carnot, right? So 1824. So what he said that any fluid may be used to operate Carnot cycle, which is performed in an engine cylinder, the heat of which is supposed alternatively to be perfect conductor or perfect insulator of a heat, right. So what is the formula for the Carnot cycle? This is a Carnot cycle. So Carnot cycle, so first process 1 to 2 is isothermal expansion, and process 2 to 3 is adiabatic expansion, and process 3 to 4 is isothermal compression, and also 4 to 1 is adiabatic compression. Here we discuss isothermal expansion, compression, expansion, 2 isothermal process and 2 adiabatic process. What are the 2 adiabatic process? Adiabatic compression, expansion, isothermal compression as well as expansion, right. So on the final output is Carnot cycle thermal efficiency is work done divided by heat supplied. So what is the work done? Q1 minus Q2, and what is the heat supplied by the source, that is called Q1. This is a Carnot cycle thermal efficiency formula. Here we discuss about one simple problem. So problems on heat engine. So an inventor claims that he is proposed of an engine the following specification. So power developed equal to 50 kilowatt and fuel burnt is 3 kilogram per hour, and the calorific value of the fuel is 75,000 kilojoules per kilogram, and the temperature limit is 27 degrees Celsius and 627 degrees Celsius. So find out whether it is possible or not, whether the inventor claims the engine or not claims the engine, or not impressed with this engine. So here we given data as P as power developed 50 kilowatt. So we take it as all the given data as given in the problem. So to find what we have to given, so efficiency of the Carnot, what is the actual efficiency and the Carnot efficiency. Okay, we go for the solution. So heat supplied equal to fuel burnt into calorific value. So what is the fuel burnt? 3 kilogram per hour into 75,000 calorific value. We get the final output 62.5 kilojoules per second. We take it into kilowatt, 62.5 kilowatt. From Carnot theorem, Carnot engine gives the maximum efficiency than any other engine. We all know that. So this is the statement the Carnot gives from Carnot theorem. Carnot engine gives the maximum efficiency than any other engine. We go for the maximum efficiency of the Carnot equal to TH minus TL divided by TH. So the maximum temperature limit is 900 minus 300 divided by 900. So we get into efficiency of the Carnot equal to 66.6 percentage. So the efficiency of the inventor we have to claim is the actual efficiency is work done divided by heat supplied equal to work done divided by heat supplied equal to, and the work done is 50 and the heat supplied is 62.5 kilowatt. We get into 80 percentage. So the Carnot cycle gives the efficiency is 66.6 and the actual efficiency is 80 percentage. So the actual efficiency is 80 percentage is the major one, that is called greater than the Carnot cycle efficiency. The actual cycle efficiency is 80 percentage, Carnot cycle is 66.6 percentage. So actual is 80. Here the inventor claims the engine has a higher efficiency than the maximum engine efficiency which is possible, right. So this is a simple example for the Carnot cycle engine efficiency. Thank you.